Hello, my dear students, and welcome to a new chapter with our course. This chapter is entitled by DC-DC converters. DC-DC converters is considered one of the most critical parts in electronic design nowadays. Regardless your level of application, either you are considering a mass or a high power level of application in a renewable energy system, or you are considering a medium energy power application, or even nowadays when you are considering a low power IoT and IoT square applications and self-powered sensors. In all these applications, DC-DC converters play an important role. Of course, the energy or some electronic design principles may differ from considering high power to low power consideration. However, the main principles will kept constant in understanding such a DC-DC converters. In this long lecture, we are going to try to understand step by step the pros of a DC-DC converter. The main focus of this lecture is actually not to analyze series of circuits that can behave to functionalize as a DC-DC converters. But I believe that the main focus in this lecture is to understand the concept beyond such circuits. Because understanding the concepts is more and more superficial with respect to analyzing circuits. In order to be an innovative electronic designer, you have to know the know-how of the circuit, not only the analysis of a circuit. So let's start this journey in order to understand the principles of a DC-DC converters. Okay, the lecture will start with an introduction about switching regulators, basis for analysis in steady state, detailed study for the basic DC-DC converters in continuous conducting mode, and then we are going to go to the study of the basic DC-DC converter in discontinuous conduction mode, DC-DC converters with galvanic isolations, and control circuitry for DC-DC converters. Let's start with the basic principle. A DC-DC converter is a stage of converting a DC voltage into a DC voltage. So your input is a DC and your output is still DC. So the idea is only to change the level of the voltage and the current of your circuit. As a very basic understanding of that, considering this circuit, as you can see, here the input is VG with a current IG, and here we have two resistance, a variable resistance and a load resistance. So basically, the voltage reaching the output will be lower than the voltage in the input due to the fact of this potential divider. And here we have a reference voltage to compare with, a comparator, and a decision-making unit. So in order to realize this circuit in terms of a physical circuit, you can replace this by simply a transistor, which acts as a switch. So what will happen is, if this signal coming from the comparator giving the high signal, this means that this switch is turned on and you connect the input to the output. Otherwise, if this signal carrying a low signal, this switch will turn it off. And then you are carrying, and then there is open circuit here, and the load or the output load will have a zero voltage. Accordingly, you can say that the efficiency of this circuit is simply the input power over the output power. The input power, the output power over the input power. The output power is V output times I output, and the input power is VG times IG. As you can see from this circuit, whenever this switch is turned on, IG and I output will be typically the same. So you can easily cancel I output with IG, and there is the efficiency is V output over VG, and it goes without saying that V output will be smaller than VG. due to this, again, potential divider. So it's a very simple way of stepping down your voltage from one stage to another. It should be a robust signal or a robust system, no electromagnetic field generation, only lower output voltage. I mean, by default, V output will be lower than V input. Efficiency depends on input / output voltages. Low efficiency because V output will not be typically equal to V input, and some bulky electronic components. So what is the process here? So then we make one step further by adding this, what we call a PWM, or a pulse width modulator here. So you know that a pulse width modulator is this circuit that produces a square wave with a variable width depending on the input signal, which is VE here. So as you can see here, this should be the input and this should be the output. The input will be VG and the output is simply a square wave. When this switch is turned on, I mean this is a short circuit, V input equal, V output equal VG, which is this case, in this higher case. When the switch is turned off, then this is a zero output because simply this is an open circuit. Nothing is connected. But please don't forget, we don't need a square wave on the output. We need a DC output. Now, from this configuration, your input will be a DC, as you can see, it's a VG voltage, but your output will be a varying square wave with a high stage called VG when this is a short circuit, and with a lower state as 0 when this is an open circuit. So what we are considering now is to add some block here so that this block, instead of getting the output and a sinusoidal output, or sorry, a square wave output as this red curve, it should get some DC variable here. So this, what we are going to do is to add a filter. Why adding a filter? Sorry, why adding a filter? It's a very simple process. You have a square wave, and back here to your Fourier analysis background. A square wave is a series of sinusoidal signals with a DC component in the around 0 frequency, and then a huge amount of harmonics. If you pass this square wave through a filter, then what's happened is you will get rid out of all these harmonics, keeping only the DC value, which represents the average value to be transmitted. The role of this filter is simply to remove all the harmonics that is associated with this square wave generated due to the turn on and off of this switch by the pulse width modulator, and only get a DC component that represents the average value of this square wave. So the next step is simply find an appropriate filter that can be now embedded here in a DC-DC converter to remove these harmonics. The start with considering a very simple filter by considering only capacitor here. So this capacitor should remove or should act as a very low order filter to remove harmonics. Now this will be the output signal. It can be easily understood that whenever this switch is turned on, I mean it's a short circuit, so the output equals to VG, as you can see, because simply you create a short circuit here. Once this switch turned off, so you disconnect the input, the capacitor will start to discharge in the resistance in this manner. So it's not as fluctuating as a square wave. However, it's not also a DC output. as you can see. We cannot consider this as a DC output. So only a capacitor will not be sufficient to build your filter. And next step is to add a coil and a capacitor. So when this is a short circuit, you will have a circuit looking like that. Once it's an open circuit, you disconnect the input, leaving the filter and the resistance. But here, a problem starts to occur. When this is an open circuit, I mean, when I disconnect here, I should close somehow the circuit so that the current in the coil or the current in the inductor should move in the resistance, and then it should return back somewhere here. But as you can see, this is an open circuit. So your circuit is not connected in the off state of a switch. That's why we reach this topology. So when the switch is turned on, now this diode is not working because simply the voltage here is greater than the voltage there. So the current is moving in the reverse direction, which means that the diode is an open circuit. And then the current is flowing in the coil and in the load, and the capacitor is charged. Once this switch is turned off, now the current flowing in the coil and in the resistance will return back, making this diode turned on as a forward bias and closing the circuit. So now this diode will complete the edge missing here, if you can get it, my students. So we reach to this structure as a very basic structure for a DC-DC converter. Now, this circuit with a coil and the capacitor working as a filter will average the signal, making your V output looks like the average component. So first of all, you get the voltage on the diode will be this sinusoidal signal, but this voltage on the diode, VD, will then filtered by this LC filter to get what's called an average signal, which is a DC signal. So in order to understand the process, we first consider this, what's called a buck converter. It's called a buck converter because, as we will see later on, my dear students, this voltage, this converter acts to buck or reduce the voltage, so the output will be lower than the input or VG here. Let's see how will this happen. So let's start with considering a steady state process and considering the signal on the output and on the input. But before that, let's consider the current flowing in the coil. The current flowing in the coil here will be either increasing if the gate, if the switch is turned on. Again, here we replace the switch by a transistor. So if this gate is a gate terminal of the transistor gets a high signal, simply this will be a short circuit, and with this will charge the coil. So in this portion of the signal, the current in the coil is increasing because it's connected to the load, till we reach a point where we reach a maximum. Then a low signal comes to the switch. This switch will turn off, I mean disconnected. Now the energy in the coil will start to discharge in the resistance and back through the diode. So this will make current go down again. In these topologies, my dear students, we consider our diode in what's called a continuous conduction mode, or CDM. Because later on in this lecture, we will consider the other type of a transistors, which called, the other types of the converters, which called a discontinuous conductive mode, or DCM. In a DCM, the current in the coil reaches to zero and remains zero for a portion and then starts up again like this. However, in the CDM, or the continuous conduction mode, the current in the coil is always above zero. It goes up and down or go in a ripple format, as you will see. So back to this configuration. And let's consider this configuration when we have an input signal. As you can see, this is the sinusoidal or the square wave input due to the diode, and this is the filter. And finally, we get the average. And as you can see, the average is below the V gate. So what about this average or V output? Simply speaking, the V output depends on how much time this signal will be high and how much time this signal will be low. We consider this in a factor which we call a duty cycle. So a duty cycle, simply, my students, is a ratio between the high period to the low period. That's why this region, we call it D times T, where T is the complete period of a signal and D is the ratio of T high over T low. So this D times T represents a percentage of the time at which the signal is high, where the complete signal is D. So you can say simply that your V output is equals to D times VG. So the higher the portion or the higher the signal is high, the higher the V output. But in all cases, my dear students, this D will be smaller than 1, which means that in all cases, V output will be smaller than V input. That's why we consider this as what we call the buck converter, because it buck or it reduces the output with respect to the inputs. Okay, but what about having a different circuit like this? Now we consider the circuit, which is considered as the buck converter. As you can see, this is another topology. We have now 2 coils, not only one. We turn the switch to be here, not there. We have also a diode. We have 2 capacitors instead of 1, and we have resistance. So this is another configuration for another converter. But before going into this configuration, my dear students, we have to understand, or I would say that we have to revise some basic concepts related to circuits. What are these basic concepts? Let's see. We have to revise actually 4 concepts. The first one is related to Faraday's law and Kirchhoff voltage law. The second one is related to the current and the voltage in a capacitor and in an inductor. The third one is related to KVL and KCL. And finally, concerning the power. So let's start. First, let's consider a coil and a capacitor. So a very important information to know that in a capacitor, in a coil, in an inductor, V equals L di by dt. V, the voltage, equals L, which is the inductance, di by dt. So in average, I mean, for a steady state, di by dt is equals to 0, which means voltage in an inductor is equals to 0 whenever you are considering average. Alternatively, in a capacitor, I equals C dV by dt. The current equals C, which is the capacitance, dV by dt. So again, considering steady state or average, the current flowing in a capacitor is equals to 0 because dV by dt is equals to 0. So this is very important to recognize in a circuit. So the second important information to know is that the total area under the curve should kept equal in a voltage or a current signal. I mean that here we have 2 levels, V1 and V2. We have the level V1 for a duration called dt, and we have the level V2 with negative in the duration 1 minus d times t. So V1 dt minus V2 1 minus dt should equals to 0, which leads that the area here and the area there are almost constant. So the wider the area, sorry, the wider the time, the lower the voltage. The lower the time, the higher the voltage. Similarly, when you consider current here, again, area is the same. The area of this triangle and the area of this triangle is also the same. Okay. Another important information, I believe you already know, which is KVL, or what's called the Kirchhoff voltage law. The Kirchhoff voltage law states that the summation of a voltage in a closed loop should be equal to zero. So if we consider this red loop, considering a VG in a positive, then we have VL1. We consider, of course, VG in positive because this is a supplier and the others are consuming devices. So VG in positive minus VL1 minus VC1 minus VL2 is equal to zero. Back to the information that the average voltage on a capacitor is equal to, on an inductor is equal to zero. Let me show it again here. If you remember, the average voltage in an inductor is equal to zero. So under steady state or under a DC analysis, you can say that the voltage here, the voltage of the first coil and the voltage of the second coil is equal to zero, leading to that all the voltage in the source will go directly to be stored in the capacitor, as you can see. So this is also another important information. A certain information to be revised, I think also you know, which is KCL, or the Kirchhoff voltage law, Kirchhoff current law, stating that the current in a node, the summation of the input current in a node equal to the summation of the output current from the same node. So if we consider node number one, for example, the current going to node number one is IL1. And the current going outside or outgoing from node number one is IC1 and IS. That's lead to the fact that IL1 minus IC1 minus IS is equal to zero. And again, knowing that in average condition, the current flowing in a capacitor is equal to zero, that makes this current is cancelled, and that makes that the IL1 average equals to IS average. Okay. So another important information related to the ideal, or what we can call a lossless system. When you have a four-port system with a two input and two outputs, under an ideal condition, you have to consider that the input power representing VG times IG average and the output power representing V output times I output, or V output square over RL, these two outputs should be equal. I mean, the input power and the output power are equal. Of course, whenever there is an ideal system, this will not happen. And we will have what's called an efficiency, that your input power and your output power are not ideal. But ideally speaking, the input power and the output power should be equal. What simply happens is, if you increase the voltage, for example, here, as you can see, V output equals N times V input, which is VZ. So what you happen is that you step up. This is, for example, a step up transformer. So you increase the current by a factor N, you increase the voltage by a factor N. Alternatively, the current will be reduced by the same factor. So in changing voltage and current does not mean changing power. Power is kept constant. However, when you change the input current, for example, increasing the current, that means that simply you decrease the voltage and vice versa. And this is also very important to be understood. Now, let's return back to our circuits, and let's start to analyze these circuits based on the knowledge we capture from the previous concepts. So, this is the first circuit. We have an input circuit called, or an input source called VG. Then we have a MOSFET acting as a switch. We have a diode, a coil, a capacitor, and finally a load. Let's start considering this. In a case where your switch is turned on, you can understand, my dear students, that once your switch is turned on, I mean, this is a short circuit, that makes automatically this point equals to VG, as you can see, and this point is grounded, which means that the diode here is in a reverse condition. So simply, you can remove this diode by an open circuit, and you can remove this switch by short circuit, leading to this circuit, as you can see. So here, we have a voltage source. Now the switch is turned to be a short circuit. The diode is an open circuit, a conductor, a capacitor, and finally a resistor. What will happen is as following. Let's start that now. This is the driving signal. I mean, the signal inputted to the gate of the transistor. So let's assume that this is in the high state. So if this is in the high state, what will happen simply is as following. The current flowing in the conductor will going to increase because now the inductor is charging. That's why IL increase. As you can see, IL and IS are typically the same. The current flowing in the switch is typically the same. The current flowing in the load in the inductor, because simply we don't have a diode here. It's an open circuit. So IS and IL are typically the same. So when IL increase, this means that IS increase as well. No current is flowing in the diode, so that's why ID is equals to 0, as you can see. So what will happen for the first cycle when the gate input voltage is 0? Now, let's consider the other condition. The other condition is simply when this gate voltage is equals to 0, not high. It's not no longer high now, it will go down to 0. So this switch will be turned off. I mean, the gate or the VG, the input source, is disconnected. And now the current will flow like that and return back to the diode. So in this case, your circuit will be looks like that. Now your diode will be a forward bias. That's why we replace the diode by a short circuit. You still have a coil, a capacitor, and a load, and your generator or your source is disconnected as far as the switch is turned off. What will happen, my dear students? Simply, let's see. First, this input or the gate, the driving signal is going to back to 0. Of course, now no current is flowing in the switch. That's why IS will drop to 0, as you can see. What about the current in the inductor? Now the inductor will discharge the current. So the current in the inductor will going to decrease, as you can see here. And as you can see, the current in the inductor is typically the same as the current in the diode, because as you know, no current is flowing in a capacitor. So the current in the inductor is typically the same as the current in a diode. That's why, as you can see here, I inductor or IL and ID are typically the same. A second round will come when this will turn on again. When the switch is turned on, your diode is turned off or reverse bias and open circuit. Now again, as you can see, a high signal coming to the gate of the switch. Then your inductor will going to charge again, same as IS, because simply IL and IS are the same. And your diode is switched off. That's why, or reverse current, reverse bias. So this is again 0. So you will have something like that. And again, a cycle of discharge. So this will be the current in a conductor or the coil, the current in the switch, the current in the diode. What about the average current in a conductor and the voltage in the conductor? Let's see. When this switch is turned on, you have some current flowing in the conductor, as we already mentioned. So the current in the conductor is going up, and this is the average. Okay. What about the voltage on the conductor? It's very simple. The voltage in the conductor, again, you know that by going a KVL, if you consider this as a loop, so this is VG equals VL minus V output. So simply VL equal VG minus V output, which is this voltage. Very simple. What about the voltage in the second cycle? When the switch is turned off and the diode is a forward bias, what will happen is simply the reverse. Again, to this circuit, the current in the inductor will drop, keeping the same average. So the average current is almost constant, as you can see. And what about the voltage in the inductor? Again, let's make a KVL here on the big loop. So VL equals V output, but with a negative sign, because VL plus V output equals to 0, which means that VL equal minus V output. That's why this is a negative sign here. So this is simply what will happen. Again, raising up and then raising down. So this is the voltage across the inductor, or sorry, this is the current across the inductor, and this is the voltage across the inductor. Now, using Faraday's law, using the fact that I equal dL by dt. So di by dt is simple. This is di, or this is the delta, or the incremental change in the current, and dt is relatively either you consider this portion or this portion. So for simplicity, let's consider the blue portion. So di over dt. What about this duration? This duration is 1 minus d times d. This one minus d times t. So di equals what? Equals the voltage, which is V output, 1 minus d times t over L. So by this equation, using Faraday's law, you can calculate the ripples in the current flowing in the inductor. Okay. So back to this circuit. Now, let's see. We already consider that the current here, the average current in a capacitor is equal to 0. If you remember, my dear students, if you remember, because as we mentioned, I equals C dV by dt. So the average, whenever dV by dt is equal to 0, that means that I is equal to 0. So by averaging, the current in the capacitor is equal to 0. That makes the current in an inductor is typically the same as the current in the load. On the other hand, and with considering, if you remember, my dear students, the area equalization process, so the area here and the area here are equal. The upper area is Vg minus V output times the duration, which is dt, minus the lower area, which is V output, 1 minus dt is equal to 0. Perfectly. So, as you can see, using this equation, we can skip d times d, t and t, we can skip both. And as you can see, also V output d in minus, and here minus V output t. That will lead that V output equal d times Vg. If you remember, we already have reached a similar formula when we consider our buck converter for the first time. And as d is typically smaller than 1, that means that V output is smaller than V input, or the generated voltage. Let's make now a KVL and KCL. Let's start with the KCL at node number 1. KCL at node number 1 will give us that IL is equals to IC times I output. IL equals IC, or IL minus IC minus I output is equal to 0. Now, as you know, the average current flowing in a capacitor is equal to 0, which means that IL average equals to I output, which is equals to V output over RL. This is a first KVL. Let's now do a power balance. A power balance means that the power input and the power output should be equals to this, should be the same, should be equal. So that means that IG, which is typically equals to IS, should be equals to I output V output over VG, because simply, as you know, VG times IG equals to I output times V output, which is the power balance. Now, you know that V output over VG is equals to D from this equation, which means that IG average equals to D times I output. Now, I'm sorry. Now, let's examine these two equations. The first equation in the red box tells us that the output voltage equals D times VG. So the output voltage will be reduced by a factor called D, which is the duty cycle. On the other hand, the input current is smaller than the output current by a factor D, or we can say that I output equal IG over D. Remember again, my students, this is a power balance. When you decrease the voltage by a factor called D, you increase the voltage, you increase the current with the same factor D, and that's create the power balance in your circuit. And this is the concept of a buck converter. So in a buck converter, we step down the voltage by a factor called D, and this D is controlled by the duty cycle. Alternatively, we increase the current by a factor D or by the same factor D. A summary of all equations related to the buck converter can be found in this slide, with considering all the KVL and KCL we done in this equation. In the next part of this lecture, my dear students, we are going to consider, or we are going to ask this question: is it possible to step up the voltage? Is it possible to get the output greater than VG? Or in other words, is it possible to boost your voltage? This will be answered in the next lecture, or in the next part of this lecture, inshallah. Thank you very much, and looking forward for the next lecture.